did we stop? What was the last problem we got to? Okay, so we did get through F. Good, 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 good. Okay, that's further than second period got. So we're on I right now. I have this for J. Just a quick recap, because several students have already been approaching me. They're kind of having difficulty telling the difference between when we're looking at a composition of functions or if we're just supposed to perform some kind of operation with them. So the composition, remember, is when we evaluate one function inside of another. You know, we've been saying all week that the output for the inside function, it becomes the input for the outside function. And then we even recently saw in a problem that that output has to belong to the domain of the outside function, right? Everybody kind of remembers this? Awesome. Okay. Well, this is what we're looking at, like f of g of x. Okay. That's our composition. We have our inner function and our outer function. What was the little notation I showed you that we could write it as instead of this? Okay, that little O, the little open circle. Okay, so we could say f composed with g of x. Okay, but if we go ahead and compare it to this one right here, this one's not composition because it's actually giving me an operation. This is simply telling me that, okay, you want to take the equations for f and g and multiply those. And I'm guessing that was the last thing we did yesterday? Okay. And like this one down here, when we get to j, this isn't composition either. What are they simply wanting me to do with those functions? Yeah, whatever operation you're provided is what you want to do with those functions. Okay, so we are on I. For what value or values of x is f of x equal to g of x? All right, so I'm going to go ahead and set these two functions equal to each other. If I remember correctly, f was negative x squared plus 3x minus 5 equals, and g of x was 1 minus 2x? Okay. So graphically, we're really just interested in the intersection between these two, the linear and the quadratic. So at most, how many solutions could I have? 2, because that's the maximum number of times that your quadratic and parabola could intersect. But is it possible they don't intersect at all? Yeah, there may be no value of x that's going to make this a true statement. Okay, so all the classes are different. 2 of them have actually solved it a way that's made me super happy. And it makes you guys super happy as well, I'm sure. Remember completing the square? Okay, completing the square is a great method if you're going to solve a quadratic equation. What else do we have? Starts with a Q. Quadratic formula, we could use that. Okay. Or what we've been doing recently, we could simply factor it. Okay. Now, as far as what you would like to do, I'm not going to hold you to a specific one. I'm not going to give you a quiz or test and say you have to solve this by completing the square. As long as you are able to solve a quadratic equation, that's all I'm interested in. Okay. So how would you guys like to do this? What method sounded the best to you? So I'll let you guys decide. You want to complete the square? Oh, I'm so happy, yay. Again, good choice, good choice. Now, in order to complete the square, I'm going to go ahead and first move everything to the same side, and then we'll kind of talk about it, because there's one condition that we need to bring up. So negative x squared. If I bring over the 2x, that would be 5x, and then I'm going to bring over the 1, so minus 6 is equal to 0. Now, completing the square, if you'll recall, this is where you're going to take half of the linear coefficient, and then you're going to square that. Okay, you're trying to create a perfect square trinomial. But there's one condition that has to be in place before you start this process. Okay, Connor, say that louder.
Oh, the x squared has to be positive.
That's exactly right. Okay, that coefficient of x squared has to be a positive 1. Anything else, you know, we'd want to go ahead and divide it out. So I'm just going to go ahead and multiply through by negative 1, change all the signs. Minus 5x plus 6 is equal to 0. Now, is there anybody out there who's like, I remember completing the square, wants to come on up and show me how to do this? No? Hey, who are we playing tonight? Okay. Oh, Savion! You were the first person. Thank you so much. I love it when a student volunteers. All right. And that's okay. You know, he's not alone up here. We're going to help him. Okay. But see, the problem is, I start to do that early in the year, and then when I really am trying to ask a question, everybody's just quiet. Nobody was going to say anything. Okay, so how are we going to do this? So are you trying to use the box method?
Yeah.
Okay, so you want to factor it.
Oh.
Complete the square, yes. I mean, if you want to go ahead and factor it, we could do that. I mean, that'll make me just as happy. Okay. We're on the right track. But remember, we're trying to solve for x, right? Okay. So this is the zero product property. So we set them each equal to 0. So one of my values is 2. That will make the equation true. Or x equals 3. Perfect. There we go. Should be getting 2 and 3. Excellent. How many people decided to go ahead and factor it? A few folks. Did anybody try to do completing the square? Raphael, did you get the same answer? Excellent. Did anybody use quadratic formula? Aiden? Okay. Did you get it? Perfect. Let me go ahead and run through very quickly because I'm sure you were all really excited to see completing the square. The first thing I would do is move the constant over. Okay. So we're going to have x squared minus 5x is equal to negative 6. You'll notice I left a little bit of room because I'm about to complete the square. Remember, what did I say I needed to do to that 5? Take half of it and then square it. So 5 halves squared, I'm going to end up with 25 fourths. And remember, it's an equation, so it has to balance. Okay. Whatever I do to one side, I'm going to do to the other. Now, this creates a perfect square trinomial. Okay. So I can factor this and write it as x minus 5 halves squared is equal to, now this would be negative 24 fourths. So combine those, I get 1 fourth. Now remember, we're trying to solve for x, so how do I get him out from under the square? What's the inverse? Square root. So x minus 5 halves would equal plus or minus 1 half. So x is equal to 5 halves plus or minus 1 half. And you can see we're going to end up getting the same response. The 5 plus 1 over 2 gives me the 3. 5 minus 1 over 2 gave me the 2. All right. Okay, now we're going to definitely see completing the square later in the year when we get to conics, but I don't know that we're going to see a whole ton of it when we start getting into trigonometry. We'll definitely see factoring quite a bit. All right, good. All right, well, let's take a look at J real quick. Find an equation for G plus P of X. All right, so remember we just said a little while ago, this is not a composition. I just want to add the two functions. G of X was 1 minus 2X, and P of X, somebody getting some text, X plus 2 over X minus 3. So if I simply want to add those guys together, I need a what? Need a common denominator. Okay, so I'm going to start with my quotient. So X plus 2 over X minus 3. Okay, plus, I'm going to say 1 minus 2x over 1. Okay. And looking at this, there we go. What is my common denominator? It is x minus 3. Whose phone is that? Somebody's very popular. Whose? Jack, is it yours?
No, I sure hope not, because I said find it and smash it.
Find it and smash it. Was this the class that I answered the phone in? There's been one time so far this year where a phone did start going off, and I answered. I was like, "Hello." I don't remember what class that was. It's really fun when a parent's trying to get a hold of the student, Okay, and like a strange man answers the phone. Hello? Like, what the heck? Who are you? All right. But anyways, now if I were to multiply those together, I'm already going to have the common denominator. So I'm going to go ahead and combine these over x minus 3. So I've still got the x plus 2. Those aren't changing. But now I got to FOIL these numerators here. So help me out. The first. So that would be plus x outside minus 3 inside. Good Lord. So that'd be a minus what? 2x squared, and last. Plus 6x. There we go. Extend that a little bit. Okay. So if you have to, write out every step before you combine them, that's perfectly fine. I like to try and do as much as I can mentally. Now let's just go ahead and combine my like terms. So the negative 2x squared is not going to combine with anything else, but how many x's do I have? Okay, so 3 terms with x, so how many is that total? So 8 x's. Okay, so, and we have our constants, which is going to give me minus 1. Now, one question I've been getting a lot, like in fact this morning during tutorials, somebody had to combine a couple of fractions, and the numerator of 1 was factorable. So the question is, do I go ahead and factor it before I combine them? And the answer is no. That is always going to be your last step, because you're going to have to combine like terms. Once you have everything together into single fraction, you've combined your like terms, you've simplified it as much as you can, this is where I would now go ahead and see if I can simplify it, because you always want to take a look at your answer. Is there anything I can do to reduce it? Now, just for the sake of time, I'll go ahead and tell you on this one. I mean, you could pull out a negative as a greatest common factor for the numerator, but it's not going to do anything to simplify the problem. Nothing's going to reduce. So that would be as far as we can go. Okay. Any questions? Anybody having a hard time? Hey, Jack. Can I not divide that? Now we could, if I were to give you this as a rational function, and I were to say, okay, is there a horizontal or a slant asymptote? Yes. But this, we're just performing an operation with the functions. So we don't have to divide that unless you just want to practice. Jack looks okay. All right, good. Well, there's one last idea that I want to go ahead and show you, and we're going to continue to work on this, throughout the year. But I want to go ahead and show you one last composition talking about its domain. So there's that circle again. Find f composed with g. So find the composition given f of x equals the square root of x minus 1, and g of x is equal to x minus 1 squared. Okay. So this is like we were doing yesterday. Remember where we were taking one function and substituting it into another? That's what we're doing here. We're finding the composition. But I want to find the domain of the composition when I finish. Okay, so let's kind of think about the domain we have right now. What's the domain of x minus 1 squared? It's a parabola that's been shifted to the right one. So are there any x's I would have to exclude? No, he's infinitely wide, right? So all reals on him. Now, the same can't be said about the radical, the square root of x minus 1. Okay, can anybody tell me his domain? It has to be 1 to infinity. Okay, now let's take a look at 1, the very first value he said. If I were to plug in 1, 1 minus 1 gives me 0. And can we take the square root of 0? Yes, the square root of 0 is just 0, right? But what happens if I plug in a value less than 1? And what happens when we get the square root of a negative? It goes imaginary. So we want to avoid those values of x that when I plug in would make x minus 1 negative. Okay, so let's go ahead and do like we did the other day. I want f composed with g, so g would be my inner function. I'm going to take this, and I'm going to plug the equation in, just like we've been doing recently. Okay, so I'll write it the way we're accustomed. F of g of x equals, so we have this square root of x, so x minus 1 squared, and then minus 1. All I did was replace x with g's equation. Okay. Now, before we go ahead and start talking about the domain, I would suggest let's go ahead and simplify it. Okay, because I mean it is in vertex form right now, one to the right, one down, but let's go ahead and expand it. In fact, it also gives us the opportunity to practice that really cool rhyme I gave you yesterday. Jane, do you remember it? No? Square the left, square the right, multiply them together, double the middle, and you got it right. Because remember I brought up, we could find something better to rhyme than right and right. Okay? All right. So what would x minus 1 squared look like if I were to expand him? Well, let's walk through it. Square the left, x squared, square the right, plus 1. Now, double the middle means to multiply the two together, so x times negative 1, and then we double that. So negative 2x. Now, that is simply if I expand x minus 1 squared. Don't forget, we still got that minus 1 hanging right there. But this one's actually pretty nice to me. What happens? Yeah, those cancel, so I can just kind of chop off the end right there. So this is my composite function, the square root of x squared minus 2x. So I'm interested in his domain. Okay. So any ideas? Hey, Jack.
Would it be everything because the square the x takes away whatever negative that is?
Now it's true, but we got to be careful because we are subtracting a value. So we could potentially have a positive subtracting a negative. So I will tell you there are values of x that we have to throw out. So it's not going to be all reals. Okay. Do we have to take out 0?
Yeah.
Well, let's see. If x were 0, 0 squared minus 2 times 0, would that be okay? Remember, can we take the square root of 0? Yes. So that's fine. So a 0 is fine. Okay. Now, in a case like this, what I would recommend, forget about the radical for a second. Forget about that square root. Focus on this guy right here. All we really want to do is avoid any values of x that when I simplify that are going to give me what type of value? Negative, because we already said 0 was okay, but if we take the square root of a negative, then it's imaginary, so he can't be part of the domain, right? So does anybody know any values that would make x squared minus 2x negative? 1 definitely would, and there's going to be a lot of others. So like I said, don't worry about the square root. Just focus on x squared minus 2x. Okay? Forget about the radical. All right? What is x squared minus 2x? What kind of graph is he? Remember, no radical, just x squared minus 2x. He's a parabola, right? Okay, what direction would he open? Up. How do we know that? Okay, because it's not a negative x squared. Can anybody tell me x squared minus 2x? Remember, this is what we're focusing on. Forget about the square root. What are his roots? 0 and 2, yes. If I were to set this guy equal to 0, I mean, we can easily see, we could pull out a GCF, x can't be 0 and x can't be 2. So we're probably going to have a graph that looks something like this. Okay. This is simply x squared minus 2x. This is where some people in the previous class got a little confused. Remember, we are not applying the square root yet. Okay? We're simply trying to analyze, I need values of x that when I plug into this guy right here will not result in a negative y, a negative value for me to take the square root of. So think back to what we were doing with the rational inequalities. Okay? What were all those pluses and minuses on our sign chart telling us? Where the graph was what? Where the graph was positive or negative. So Jack, what do you think?
Could you say negative infinity, 0 is unique with 2 to infinity?
That's exactly right. Because a minute ago, didn't Aiden say that 1 was a number that if I plugged in is going to give me a negative?
No.
Okay. So 1 squared minus 2 times 1 would give me negative 1. So definitely 1 has to be thrown out. So looking at this quadratic here, I wouldn't want any value of x that's going to result in a negative y value. I'd only want to focus on where this graph is positive. So Jack is absolutely right. Okay, I'd only want those intervals right there from 0 to 2. Now let me go ahead and write this out. The domain, negative infinity to 0, union 2 to infinity. Would I include the 0 and the 2? Okay. So we think no, or now you change your mind. Okay. Well, let's see. If I were to plug in 2, 2 squared, 4 minus 2 times 2. 0. And can we take the square root of 0? Yes, that's fine. So I would include those. So it's only this little interval here, not including the 0 or 2. We have those in our domain. Any value of x between those would make the radicand negative. So if I were to take the square root of it, it would go imaginary. We'd have to throw it out. Is everybody okay with how I reasoned my way through that? How I used the radicand to figure out where he was positive and negative? Okay. Oh, we got plenty of time still. All right. So let's try one on our own. Okay. Let's try this next one. Find the composition f composed with g given f of x equals 1 over x, your rational parent. Okay. And g of x is equal to the square root of x squared minus 1. Okay. All right. So I want you to find me the composite function, but also tell me what his domain would have to be. Okay. And think about what we did on the previous example. Okay. So the last thing you'll be looking at is that square root, so you should be able to get to the root of the problem. You'll laugh later. It's always later. Now, you may not be done, and that's okay. All right. Let me go ahead and start to catch up with you folks. All right, so just like before, okay, I want f composed with g, so I'm going to take g's equation and plug it in. So f of g of x is going to be 1 over this square root of x squared minus 1. All I'm doing is replacing the x with that function. And, you know, we could go ahead and rationalize it because we don't like radicals in the denominator, but I'm not really worried about that right now. Okay, so we'll just go ahead and leave it like this. 1 over the square root of x squared minus 1. Okay, now what I'm interested in is the domain. How many people think they have the correct domain for this composition? Okay. Or, let me rephrase the question, how many people have an answer, but they are not 100% confident in it? Okay, so I got a few hands going up. Okay, all right. Well, Stephanie, would you want to help me out? Yes. What do you think? What do you believe it is? Okay. And do we include those values or not? The negative 1 and the 1. So we do include them. Okay. Well, let's take a look. Now, here's the thing. This time we want to focus on x squared minus 1. Okay. We still have the square root of a quadratic, so forget about the radical right now. Focus on x squared minus 1. I'm interested in values of x that will only make x squared minus 1 positive. So let me go ahead. I'll just draw some axes real fast. It definitely opens up. In fact, what is the one transformation that's happened to x squared? Yeah, it's just been shifted down 1, right? So we're going to have a graph that looks something like this. What are its roots? Negative 1 and 1. Okay, just like Stephanie said, perfect. Because if you set x squared minus 1 equal to 0, okay, those are the values that make it true. Now here's the thing. Again, we only want values of this that are positive. So I need to eliminate any portion of the graph that would result in a negative expression, because we don't want imaginary. Right, Xavier? Right. So she did say from negative infinity to negative 1 and 1 to infinity. There was just one little detail. The question of will we include them or not. Now, can we take the square root of 0? Yes. So why is this one different? It is a radical, but where is it? It's in the denominator. So while we still can take the square root of 0, here we would not want to include those because that would make it undefined. Excellent, excellent. How many other people had that? See, now I'm starting to see more hands go up, okay? Even with the parentheses? So Dylan, why didn't you raise your hand? Okay, Rhett? You gotta have confidence. I stand up here all the time. How many times have I been wrong? Very rarely, right? Now you're laughing. I like that. But it does happen, okay? All right. Doesn't matter if you're wrong. That's why we're doing this. We're going to learn. Okay, so let's go ahead and, good Lord. Ah! This one's lit up. And it's got a pineapple on there. Whose is this? Oh, no, that's not it. Good Lord. But isn't everybody on remind? Yeah, but everybody else who doesn't have their phone off, here we go, bleep, 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 or whatever it does. Oh, okay, anyways. All right, let's go ahead and take our quiz. Clear your desks for me, please. All right, we got that, we got that. Okay, we are ready for the next class.